Hi everyone, welcome back to our discussion. In the last video we discussed electric potential energy and how this can be used to solve things like conservation of energy problems and figure out other things about the behavior of charged particles in electric fields. Today we're going to turn our attention to the electric potential, that is, the potential energy per unit charge. So you can think of an electric field as the force on a charge by sources equals the charge times the alteration of space by those source charges. And you can also come up with this idea that potential energy of a charge plus sources equals charge times the potential for the interaction of the source charges. Well, what is that potential? That's what we're going to be turning our attention to in this video. So the electric potential is defined as the electric potential energy involved in your system, including your test charge, divided by the value of your test charge. And we're doing this in such a way that we don't end up, that our test charge is small enough that it doesn't end up altering the configuration of the source charges themselves. So from that, we can say that if we do bring a charge into a region of a certain electric potential, the electric potential energy that is now present for that charge is equal to the charge times the electric potential. So the electric potential, being the electric potential energy per unit charge, is dependent on the electric fields that are there due to that charge configuration. And with that in mind, you can also think of a gravitational potential, that is the gravitational potential energy per unit mass, and it would be dependent on the gravitational fields present due to the mass distribution. So the gravitational potential would simply be equal to the gravitational field strength, that is the acceleration due to gravity, times the height, where that height is a change in position relative to some zero value of gravitational potential, which is usually taken to be the ground level. Notice that there is not a mass multiplying this. In other words, gravitational potential energy would be what you would get if you multiplied the mass. Now this would be assuming a uniform gravitational field strength. If this field strength is not uniform, then the real equation is the gravitational potential is negative big G times big M, where big M is the mass distribution, divided by R, where R is your distance from the center of this mass distribution. Now, back to electric potential. Electric potential is used so often that we've actually come up with special units for it instead of just coming up with, say, like joules per coulomb or something like that, which sometimes people state it as joules per coulomb, but people decided that it's so important and so ubiquitous that it needs its own unit, which we're going to call the volt, given by the symbol capital V. Now, keep in mind a potential, no pun intended, source of confusion. The symbol for electric potential is often capital V. The symbol for its SI units is capital V. Now, the typical way that we get around this is that when we write symbols for quantities, we always italicize the symbol, whereas symbols for units are never italicized. So that's the usual way that we get around this. Another way of getting around this is that sometimes people call the electric potential by the symbol of the lowercase Greek letter phi, but we're not going to do that. That's not all that common in high school physics, even in AP Physics C, E, and M. But keep in mind that is sometimes done. Lowercase phi is sometimes given for the symbol as the symbol for electric potential. Now keep in mind that electric potential is always present. Whenever you have some sort of source charges around that create electric fields, there is electric potential present, whether or not you actually put charges there to experience it and get moved by it. So keep in mind that the potential difference is typically given as the final potential minus the initial potential. So when something goes down in electric potential energy, we have that delta V is less than 0. That's something that will become especially important when we talk about circuits. Now, let's turn our attention to using electric potential in solving conservation of energy problems. In a manner of speaking, we've already done this. It's just that now, instead of talking about it as electric potential energy, we're going to realize that that electric potential energy can be substituted by the charge in question times the electric potential there. Why would we do that? Because usually it's electric potential that is actually controlled. You set two electric terminals to have an electric potential difference of 6 volts. Boom, you have just set the electric potential by attaching them to batteries. Now when we're solving problems, we're generally going to start with conservation of energy first. That is the proper way of dealing with it, even though in our physics textbook they kind of start with the third step. But generally speaking, it's best to show people, hey, I'm using conservation of energy. What does that mean? It means that the kinetic plus the potential energy is equal to the kinetic energy plus the potential energy at the end. In other words, that total is constant. What does that mean? Well, now is where we substitute in the fact that potential energy is charge times electric potential. And then, of course, substitute in proper terms for kinetic energy as well, assuming that this is translational kinetic energy. If there was also rotational kinetic energy to deal with, we'd have to add in a plus 1/2 I omega squared. But you've done that back in kindergarten physics. So keep in mind that our textbook tends to put the final term first and the initial term second. I've reversed that because in terms of time, temporally speaking, initial comes before final. So the idea is that what you have at the beginning must equal what you have at the end. So also I have abbreviated something here. Quite often we're dealing with multiple charges. So where I put in a capital K, that could potentially have been replaced by a sum over K. In other words, total kinetic energy and even total potential energy as well. So just keep that in mind. Sometimes we just eschew the summation symbol, even though we really mean it to be there. When it becomes clear is when we write out the individual terms, potentially in the next step. Also, be very careful about the sign of the particle. A favorite AP exam trap, especially on the multiple choice section, is for them to talk about an electron, or say like a fluorine ion that has had an electron added to it or something like that. And then the particle would be negatively charged. It would have a net negative charge. So in that case, it's actually going to have an electric potential energy that would have opposite sign as what you would think. But the electric potential would be the same regardless. The electric potential is created by the source charges that are creating the electric fields to begin with. Let's look at an example. Let's say we have a proton fired with a speed of 200,000 meters per second from the midpoint of a capacitor toward the positive plate. So first, we're asked to show that this is insufficient speed to reach the positive plate. And then the question is, what is the proton speed when it collides with the negative plate? So, the initial electric potential. We showed already that the electric potential is proportional to position in a constant electric field. And this is a constant electric field. Now, if you're not convinced right now that this equation is true, then keep this in mind. Since it's a constant electric field, remember the fact that the change in potential is equal to the electric field times the distance in a constant electric field. So if the change in potential from the negative plate to the positive plate is equal to E times D, where D is the separation distance between the plates, then the change in potential from the negative plate to where we start is going to be equal to E times S, where S is the distance from the negative plate to where we start. So just keeping in mind that the E is the same E, we can make a substitution there and come up with the idea that the electric potential at the place where we're starting is equal to the ratio of the distance from the negative plate to where we're starting compared with the separation distance between the plates times the potential difference between the plates. So it's kind of an application of ratios, where we use the fact that since delta V is equal to E times S, or E times D, and that would mean that the E is equal to delta V divided by D, then we just say, hey, the electric field is the same, so delta V divided by delta V divided by D is equal to the initial electric potential V sub I divided by the initial position S. Anyway, we're told that it's 500 volts because we look at the picture, we see that the negative plate is called 0 volts, the positive plate is called 500 volts, and we're also told that it's halfway between. We're not told any distances, all we're told is that it's halfway between the negative plate and the positive plate. In other words, S over D is equal to a half. That's why we wrote it like this at the beginning. We anticipated that. So yay, now we know the initial potential is 250 volts. Now it's time to do some energy conservation. So we write out some givens. This is a proton, which has the mass of a proton and a charge of an elementary charge. And the initial potential is 250 volts. The final potential, assuming it meets the plate on the right, is 500 volts. We are going to assume that it actually does hit the plate on the right, the positive plate. And then we're going to see how fast it goes when it hits that plate. It might turn out that we'll reach a contradiction. Let's find out. So what's the proton's speed if it reaches the positive plate? So there's the proton's charge, one elementary charge. So conservation of energy, total initial energy equals total final energy. Here we have one particle, so kinetic plus potential energy initial is equal to kinetic energy final plus potential energy final. And then we substitute in the terms here. Notice that this time when we substituted in for electric potential energy, we wrote it as Q times V. We're not told the electric potential energy, but we are told the electric potential. And we know that it's a proton, so we know its charge. And we're interested in what the final speed is, V final. So there we go. Uh-oh, I've gone to small font. Must be a lot of math. Uh-oh, run away, run away. Divide both sides by a half m. Move the 2qVF over m to the other side so that we can solve for the V final squared. Take the square root. And then plug in the numbers. And when we plug in our numbers, we notice that there's a possibility for a negative term under this radical because we have a 250 minus a 500. The question is the 200,000 meters per second big enough to overcome the negative result that we're going to get from this term? Turns out it is not. When we plug in our numbers, we get a negative 8 times 10 to the 9 meters squared per second squared. So the final speed is imaginary, meaning that our assumption that the proton reached the positive plate was wrong. So how fast is the proton traveling when it reaches the negative plate? So we take the same equation that we just derived. That's another good reason why you should derive your equation in terms of variables only before plugging in any numbers, because a lot of times you might be able to reuse that and not have to go through all the previous work. So it's the same situation, just with a difference in potential. Instead of a difference of 250 volts, now we have a difference of negative 250 volts, and that's going to make all the difference for us, because when we plug that in, initial minus final being the negative difference, we get a positive 250 for our V initial minus V final, which means everything under the radical is going to be positive, and it's all going to add together, and we get a speed greater than what it was before. Originally it started off at 200,000 meters per second, but it hits the negative plate at 300,000 meters per second. What about a situation of an electron placed at rest, 37.5 centimeters from a fixed point charge of negative 2.6 picocoulombs? What's the electron speed when it's very far away? Well, this is one of those escape problems from similar to the previous video where we were just talking about electric potential energy, but here we're going to solve the problem in terms of electric potential. So we have the point charge, which we're calling big Q, we have the electron, which we're calling little q, and using conservation of energy, we have kinetic plus potential initial equals kinetic plus final potential final for energies. and then plug in the electric potential energy in terms of the electric potential. But we know the equation for the electric potential of a point charge. So we solve for our final velocity. We're going to plug in this V initial, this capital V initial being K big Q over R, where big Q is the charge of the object that's creating the field and thus causing the potential. When we plug those numbers in, notice we have a negative for the source charge, but we also have a negative for the electron. So they do repel each other. Like charges repel. So when you work out the numbers, you get that infinitely far away the electron will be traveling at 1.48 times 10 to the 5th meters per second. Now, notice that again we plugged in the electric potential at the point where the electron was, at a distance of little r. That is the distance between the source charge and the electron. In other words, it was due to another charge. And in general, it will be due to other charges, though in this particular example, it actually was only due to another charge. But in general, we're going to be dealing with situations, say, like capacitor plates. They're going to be dealing with multiple charges. But the potential is due to other charges, not the particle itself that we're examining. Now, when dealing with capacitors, recall that the electric field inside a capacitor is constant. The point is, it is constant. And since it's constant, and we also recall that the electric potential increases as we get farther and farther up into the electric field, that's going to give us a linear increase in electric potential. Now, just a reminder that that symbol eta that we use for surface charge density is often used as lowercase Greek letter sigma on the AP exam. But since the electric potential energy of a charge is QES, where S is the position, basically the distance from the negative electrode, where we're calling the position of the negative electrode 0, we have that the electric potential is V equals ES. In other words, potential is potential energy per unit charge. So we divide out the Q, and there we go, ES. In other words, as you go from the negative plate to the positive plate, the electric potential goes up in a steady rise. It's a constant slope because it's a constant electric field. Constant field, constant slope, kind of starting to remind me of a derivative there. Is there a relationship between the derivative of a potential and the electric field? Turns out indeed there is, and that's going to be the subject of Chapter 29 discussions. But for now, we're just going to notice this, and notice that the difference between the potential of the negative plate and the potential of the positive plate is simply the potential difference between the plates. While that's a tautology, that's also what is typically measured. What you're measuring is the difference between the plates, not usually an absolute electric potential, unless it's grounded, that is set to be 0 by touching it and connecting it with a conducting ground. Now, more about pictorial representations. So, equipotential surfaces are a very common tool that physicists and engineers use to visualize what's going on with electric fields. So, the potential graph and the contour graph are two representations that are in such common use because they're actually very easy to draw. So, keeping in mind that the electric field is always perpendicular to the electric potential. In other words, the electric potential is telling you the direction at which the electric field is, the electric field is telling you the direction in which the electric potential is most rapidly decreasing. That means that lines of constant potential are always going to be perpendicular to electric field lines. Here are some examples. Consider the electric field and the electric potential of a point charge, like what we have on the far left. In that case, the electric field is going straight out. The equipotential lines in this two-dimensional representation are just circles. But in full 3 dimensions, they would be spherical shells. In the case of a dipole, where we have this nice centipede diagram for the electric field, the equipotential surfaces are 2 sets of almost concentric, almost circles. But they're not perfect circles because of the fact that the electric field at one charge is being influenced by the electric field from another charge as well. So things end up getting stretched out because of that. What about identical positive charges? In this case, we have, actually this is the real centipede diagram, the other one's more like a cockroach diagram or a ladybug diagram. But here, the equipotential surfaces, first they start off as something kind of like circles, and then they have this crossing with the infinity sign, and then after that it starts to be more ovals that encircle both charges. And as you get far enough away, those ovals will start to look more like circles. Now, the point about these curves, these blue curves, are that they are curves of constant electric potential. So, because of that, if I tell you that a charge is at this spot over here, and it is released and goes to some other spot, well, let's start farther in. Let's say that the charge is over here, and it's released, and it goes to some other spot. As long as we know what equipotential surface the charge was on when it was released, and what equipotential surface the charge was on when we measured it later, then we could use conservation of energy to figure out how fast that charge is going to be going. Now, these equipotential surfaces will become real things when we talk about conductors later on in this unit. So here is basically a potential graph on the left where we have the electric potential as a function of position, and then actual equipotential surfaces where the 0.5 and 1 volts are imaginary surfaces drawn in there but in multiple dimensions. And then here we have the contour map, which is what you will often be drawing, say like on the AP exam, in labs and stuff like that. And then something kind of like an elevation graph with the reminder that these parallel plates are actually each multidimensional objects. Now, when we're dealing with these capacitors, keep in mind that we create the electric potential difference in the capacitors. That difference, delta V sub C, is defined as the potential of the positive plate minus the potential of the negative plate, which also is equal to the electric field times the plate separation, as long as the plate separation is small compared with either of the dimensions of the parallel plates. So using that allows us to figure out the electric field in practice, because usually we don't know the surface charge density, but because we can use this to figure out the electric field, we can deduce the surface charge density after figuring out the electric field. The reason that's important is because it's electric fields and high electric fields and high surface charge densities that can cause dielectric breakdown, which is something that we'll get into later in this unit. So, since the electric potential energy of a charge in a plate capacitor is QES, where S is the distance from the negative electrode, then we simply set the potential to be 0 at the negative electrode, and then have it going up in uniform increments until, well, roughly uniform increments, until we get to the positive plate. So, they are uniform increments, it's just we didn't have the distances exactly right in here, as you might be able to tell. And again, this is a bit analogous to the fact that as you get higher and higher in a gravitational field, you get a higher and higher gravitational potential. Now, keeping in mind the real equation for gravitational potential always being negative, what we mean by higher and higher is closer and closer to 0, less and less negative, that is. It doesn't really matter, though, because if you drop the object, it's going to be gaining a positive amount of kinetic energy as it loses potential energy. Now, keep in mind what all this stuff about contour maps and everything actually means. See, we're often required to find or state the direction of the force on a charged particle, Well, a positive particle will experience a force that's in the same direction as the electric field. That is, from higher electric potential to lower electric potential. In other words, it naturally goes down the waterfall. Whereas a negatively charged particle actually naturally climbs up the waterfall. We don't have anything analogous to that in mass as far as we know, but in the case of a negatively charged particle, it's going in the opposite direction to the electric field, which means a negatively charged particle will naturally go from lower electric potential to higher electric potential. So when you're trying to figure out the force and you've got to state the direction, keep in mind what the charge of the particle is. I know that I've stressed that a number of times, but that is a common type of task on the AP exam, especially in the multiple choice section. So we already came across this equation for the electric potential inside of a parallel plate capacitor at a certain distance s from the negative plate. Now, examining this a little bit more closely, we realize that since the potential is proportional to s, then we simply could get that by the ratio method as opposed to the analysis of saying, hey, the electric field is equal and stuff like that. So, with all of this in mind, let's take a look at an important example. Let's say you've been assigned to work in a lab with a small proton accelerator, and your task is to measure the speed of the protons as they emerge from the accelerator. And we're assuming that the accelerator is accelerating them to constant speed. If it's not perfectly constant speed, then we'll get some scatter in our data. So, in any case, to do this, you're going to decide to measure how much voltage is needed across a parallel plate capacitor to stop the protons. In other words, if you increase the voltage high enough, they're going to end up not being able to climb up that waterfall, so to speak, even though they've been shot at a high speed, and they will turn around at a certain point. So you use a capacitor that has a 2 millimeter plate separation, and you fill the space between the plates with a low-density gas that allows you to observe, at least microscopically, a slight glow from the region where protons are colliding with and exciting gas molecules. And the width of this glow will tell you how far the protons travel before being stopped and reversing direction. This is actually an experiment that is sometimes done in introductory physics labs, particularly at colleges and universities. And you don't even need a microscope in that case. The gas is just air, and the glow is an easily observed kind of bluish-purple or purplish-blue glow. So, in any case, based on the width of that glow, that is how far the glow goes from the negative plate to where it stops, you can deduce you can use this multiple times to deduce the speed that the protons are entering into the plate capacitor. In other words, what you're going to do is you're going to vary the voltage. As you vary the voltage, that changes the width of the glow. Let's see how. So the idea is use these data, as you have varied the capacitor voltage, to change the glow width. Use these data to figure out the speed at which these protons are entering between the plates. So, because of our ratio relation, we recognize that the electric potential at S, compared with the potential difference in the capacitor plates, is equal to S over D, where D is the separation distance, which is fixed. S is the glow width. S is how far the protons go before they're turned around. In other words, before they reach a zero value of kinetic energy. So that S is going to be the glow width. So from conservation of energy, we use the fact that initially it's all kinetic, at the end it's all potential. So we find the relationship between the final electric potential and the initial speed of the protons, like this, where we have 1/2 mv squared for initial kinetic energy, a Q capital V final for the final potential energy. So that V final is the V that we're going to plug in on the left side of our V equals S over D times V sub C. V final, in other words, is based on how far it actually gets. V sub C is what we set the capacitor voltage to be. So we have our equation for V final. but that's the final potential that the protons reached before being turned around. So that's the potential that they have after traveling a distance s. So we're going to substitute that v final into v in the v equals s over d times v sub c equation. So when we do that, we get this result. So now let's see. Well, m, that's the mass of a proton, that's a constant. Q is the charge of a proton, that's a constant. S is something that we measure, that's the glow width. D is something that's fixed, that's the 2 millimeter plate separation. And V sub C is something that we actually change. In other words, V sub C is the independent variable, and S is the dependent variable. V initial, that's the speed that the protons have entering the plate. That is a constant, presumably. Now, it turns out it's going to be a little more straightforward to pretend that S is the independent variable and just graph capacitor voltage as a function of S. But what we need to do is we need to solve for capacitor voltage. So what we're going to do is we're going to multiply both sides by little d, divide both sides by S. And when we do that, we recognize that the capacitor voltage is inversely proportional to the glow width. In other words, of course, what we're really doing is we're changing the capacitor voltage, but in any case, we increase the capacitor voltage, we decrease the glow width. So, since they're inversely related, it would not make sense to make a linear plot. If you plot V as a function of S, it's just not going to work. You would end up getting an inverse function curve, and you wouldn't really be able to do any sort of best fit with that. But the point is, we're not going to graph V sub C versus S. We're going to graph V sub C versus 1 over S, and recognize that the slope of that graph is going to be equal to the plate separation d times the mass of the protons p, or m, times the initial velocity squared divided by twice their charge. And from that, we're going to obtain an equation for the initial velocity that they have. So, since the slope is equal to this, solving for the initial velocity in terms of slope, well, slope equals this expression, so multiply both sides by 2q, and divide both sides by d times m. Then we have that v initial squared equals 2q slope divided by d times m, and that is d times m. That's not a differential. If you think that's a derivative, go directly to jail. So, take the square root, and we get the initial speed of the protons. All we need to do is make our plot and find its slope. So let's do that. Well, in order to do this, we need to make a new column. The idea is we're plotting V sub C versus 1 over S. Well, V sub C is there. That's the capacitor voltage. We need a column for 1 over S. So, after making a column for 1 over S, where S is the glow width, we now have everything we need to make a plot. Now, first of all, I'm going to warn you, I cheated here. I used Microsoft Excel to create this plot. And I used Microsoft Excel to find the slope of this plot. You, presumably, will not have access to Microsoft Excel on the AP exam. In addition, on the AP exam, one of the things that they're mainly interested in checking your ability is your ability to hand plot these sorts of situations. And from your hand plot, draw a best fit line. The idea is you want to draw a line that kind of best represents your data so that you have it basically having the same slope as the data seen at large and roughly an equal number of data points on each side of your line. Now also, when you draw such a thing, you have to calculate the slope. Absolutely do not calculate the slope using data points. Because after all, for one thing, it might not even go through 0. For another thing, anytime you do calculate the slope using any data point at all, they check it very, very carefully to make sure that that data point is on the line of best fit. Instead, what you actually need to do is pick 2 points from the line of best fit, which are not generally data points, and use those to calculate your slope. Now it just so happens that this central point right here kind of is on my line of best fit, so I could potentially use like the first point and the third point and get a rough estimate. But I would be very careful on that. I would highly recommend just extending the line in both directions and finding points on the graph that you can easily identify and use those to calculate the slope. But in any case, pretending that we found, say, like some point over here and some point down over here and use those to calculate a slope of 1.5742 volts times meters, units are on slopes too, then we can plug that in along with our givens and the mass of the proton, the plate separation d, to obtain the initial velocity of our protons as 3.9 times 10 to the 5th meters per second. Now I do want to bring your attention to something. Notice how in this example, just going back to our derivation, we combined results for that we got from conservation of energy back over here for our electric potential with a result that we had already obtained for electric potential. In general, it is very common to combine together results to obtain a new equation, not just in this unit, but in physics problems in general. So keep that in mind. That is something you will likely need to be able to do on an exam. Now, before we turn our attention to harder problems involving calculus, let's examine the electric potential of point charges. In particular, we want to look at the electric potential due to multiple point charges, because this is what's going to lead us to an understanding of how to deal with the electric potential of continuous charge distributions. So just remember that, long story short, electric potential is electric potential energy per unit charge, but the electric potential is something that is caused by the presence of an electric field. So with that in mind, sometimes it's useful to recast the equation for the electric potential of a point charge as just the electric potential of some particular point where it's been evaluated times the ratio of the inverse of the radii. In other words, you might wonder, it's like, how is this the ratio of the inverse of the radii? Well, it is, because if I've evaluated the potential as V0 at point capital R, then the potential at some other point is equal to V0 divided by little r over big R. And I just rearranged that equation to make it look like this. But remember, since electric potential for a point charge is proportional to 1 over radius, the ratio of electric potentials due to that point charge is equal to 1 over the ratio of radial positions. What is it for multiple charges? It's the same thing. In other words, the superposition principle applies. Let's take an example. Let's say we have 4 charges, Q1, Q2, Q3, Q4, spread symmetrically about the origin on the traditional X and Y axes. Question is, how would we rank the electric potentials at points A, B, and C? So first of all, without any calculation, we can see that obviously the electric potential at point B is greater than the electric potential anywhere else. And also we can see that since point C is closer to our point charges in general than is point A, after all, point A is really far away from Q3, whereas point C is closer to Q2 and Q3 than point A is to anything except for Q1, where it's tied, and point C is also closer to points charges Q1 and Q4 than point A is to charges Q2 and Q4, let alone Q3. So the potential at B is greater than the potential at C, which is greater than the potential at A. This all worked out because these are all the same charges, so we didn't need to worry about any weightings due to different magnitudes of charge. What if the charges are different? Well, in this case, we'll keep the charges the same magnitude, but we'll make charges 1 and 3 positive and charges 2 and 4 negative. Well, in that case, the electric potential at point B is 0. electric potential there is 0 because it gets positive contributions from Q1 and Q3 and equal magnitude negative contributions from Q2 and Q4. So those cancel. What about the other points? Well, point C is equidistant from two opposing charges. Q2 is negative, Q3 is positive. So since it's equidistant from both of those, and there is no vector nature of electric potential, then the electric potential contribution from point charges 2 and 3 at point C cancels. Same thing happens for the electric potential contribution of charges 1 and 4. Those also cancel because those are opposite charges that are equidistant from point C. The only one that's not 0 is actually the potential due to charge A. At point A. The point A is closest to Q1, which has a positive electric potential. It's farthest from Q3, which also has a positive electric potential. So you might wonder, well, what about Q2 and Q4, which are both negative? Well, if we say that the distance from point A to charge 1 is 1 unit, then the distance from point A to charges 2 and 4 is square root of 5 units. Well, square root of 5 is more than 2. So even though there are two of these charges, the fact that it's more than twice as far away from each of them, remember electric potential goes as 1 over distance to the first power, means that the electric potential contribution due to charge 1, that positive contribution, more than cancels out the negative contributions from charges 2 and 4. Plus we also get a small positive contribution from charge 3. So the electric potential at point A is positive, but the electric potentials at points B and C are both 0. So that's how we would rank those. So just as with the electric field of a point charge, the potential due to a point charge is set to be 0 infinitely far away. But because of the fact that the electric field is a vector field, making a lot of mathematical calculations particularly tedious, a difference from that is that the electric potential is a scalar field. We don't have any vectors coming into it. Going back to this example, no vector signs came into this at all. In other words, all that mattered for the electric potential, say at point C, was that the fact that, okay, point C is a certain distance from charge Q, that's one contribution. It's a certain distance from charge 3, that's another contribution. And it turns out that since those distances were the same and the charges themselves were opposites, the net contribution for the electric potential at point C due to charges 2 and 3 was 0. And same for charges 1 and 4. So this makes the mathematical calculations often a lot easier. Likewise, these calculations will also be easier when we examine the electric potential due to continuous charge distributions, where we replace the sum with an integral sign. We bring out the constant stuff. We realize that the distance will itself depend on a particular charge, so we keep that inside of the integral. And that is something that we're going to look at in more detail with some examples in the next video. I'll see you then, and thank you for watching.